Imagine turning a dense, theoretical AI research paper into fully functional code in just minutes. Today, we're looking at an AI that does exactly that for computer vision.
Yeah, it's honestly a complete game changer for the field.
Welcome to our podcast, Artificial Intelligence, papers and concepts curated by Dr. Satya Malik and narrated using AI-generated voices.
I am really excited to get into this one. It's such a fascinating topic.
It really is. So our focus today is this wild paper titled NeRFify, a multi-agent framework for turning NeRF papers into code. And the mission here is to explore how researchers at UC San Diego built this, multi-agent AI system that doesn't just read complex computer vision papers, but it actually builds, runs, and visually tests the software described in them.
Right. And to really grasp why this is such a huge deal, we kind of need to establish the baseline of what a NeRF actually is. So NeRF stands for neural radiance field. And it's basically this method for generating highly detailed 3D scenes from just a sparse set of standard 2D images. So, imagine you take a few dozen regular photos of a glossy apple from various angles.
Just flat 2D photos,
Yes,
right?
exactly, just flat photos. The NeRF uses a neural network to synthesize completely new views. So it lets you smoothly fly a virtual camera through a 3D space that it's synthesized entirely from those flat images.
I just want to make sure we're totally clear on the mechanics here because it doesn't just build a standard 3D mesh like you'd see in traditional computer graphics, does it? The literature specifically mentions it optimizes a continuous 5D scene representation, which, why 5D? We live in a 3D world.
Yeah, that 5D aspect is kind of the secret sauce. So 3 of those dimensions are just your standard spatial coordinates, X, Y, and Z. That just tells the system where a specific microscopic point is located in physical space.
Right, the 3D part.
Exactly. But the other 2 dimensions, they represent your viewing angle, theta and phi. So think about that glossy apple again. The white glare of the light on its surface, it changes depending on where you are physically standing.
Oh, because of the reflection.
Exactly. By factoring in the viewing direction, the neural network essentially learns to render complex, view-dependent effects, stuff like reflections, refractions, and shadows.
This podcast is sponsored by BigVision.ai, a consulting and product development company that helps companies of all sizes build computer vision and AI solutions. You can reach them at contact@bigvision.ai.
It's honestly incredible technology.
It really is. And since that original paper introduced this whole 5D approach back in 2020, there have been, over 1,000 follow-up papers published.
Oh, easily thousands.
But the source material highlights the severe reproducibility crisis in the field. So why is this specific area of computer vision so difficult for other researchers to actually replicate?
Well, the biggest issue is that the vast majority of these papers, they simply do not release their source code.
Wow.
Yeah. So if you're a researcher or an engineer listening to this, and you want to use a new NeRF technique, you have to manually re-implement the entire thing using literally just the mathematical formulas printed in the PDF.
That sounds like a nightmare.
It is a nightmare. It takes, 1 to 2 weeks of just grueling, highly specialized effort, because you're dealing with really complex volumetric rendering math that is tightly coupled with neural network optimization.
Right.
So a single misplaced mathematical activation function, or say an incorrect ray-sphere intersection calculation, it just causes catastrophic failures.
Actually, the notes mention NaN gradients as a super common failure state. I've seen that term thrown around, but what is physically happening inside the code to trigger that?
Right. So NaN stands for not a number. It basically happens when the math completely blows up. Like, let's say your code slightly miscalculates the distance a virtual light ray travels, right? And that results in this microscopic divide by zero error. Yeah. In a standard program, that might just throw a quick error and stop. But in a neural network, that infinite value cascades backward through millions of parameters during the training phase. It instantly corrupts the entire network, and your training run just hits a brick wall.
Just from one tiny divide by zero error.
Exactly. Or sometimes it converges on what we call a degenerate solution, where your rendered scene just looks like a blurry cloud of static. And considering that training takes 24 to 48 hours on high-end GPUs, making a tiny tweak and then waiting 2 days just to see a static cloud, it makes debugging absolutely agonizing.
Okay, let's unpack this for a second. If writing and debugging this code is so incredibly tedious, my immediate thought is to just outsource it. We have systems like OpenAI's O1 model. Why can't we just feed the PDF into a cutting-edge general AI and just ask it to output the Python code?
Well, you'd think that would work, but the data explicitly shows those generic frontier models just fail terribly at this specific task.
Really? Even the best ones?
Yeah. According to the benchmark tests conducted for this paper, the best performing general system, which is O1, it only hits a 26.6% accuracy rate on complex machine learning papers.
Wow, compared to what, like 40-something% for humans?
Exactly. Humans are at 41.4%.
Yep.
And it gets worse. When we look at the specific NeRFify bench test that evaluate these complex NeRF implementations, generic systems produce trainable code only 5% of the time.
I mean, a 5% success rate is practically statistical noise. What is the fundamental disconnect there? If an LLM can write complex Python for a web server, why does it completely faceplant when it comes to computer vision code?
It's because generic LLMs, they might spit out perfectly valid Python syntax, but they completely lack the domain-specific architectural understanding. They don't intuitively grasp the physical constraints of light and 3D space.
Gotcha.
For example, the source notes highlight these cases where generic AI models try to implement a paper that calls for a planar factorization.
Okay, let's actually break that term down for the listener. What does planar factorization actually do in a NeRF?
Sure. So storing a full 3D grid of high-resolution spatial data requires massive amounts of computer memory. Planar factorization is basically a spatial compression trick. Instead of storing the full 3D volume, you mathematically squash the data into intersecting 2D planes.
Oh, okay, so it saves memory.
Exactly. But when a generic LLM reads a paper requiring this, it often doesn't understand the spatial geometry involved. So instead of writing the complex tensor operations to intersect those 2D planes, it just falls back on its generic training data.
Let me guess, it just throws a standard neural network at it.
Bingo. It inserts a standard multi-layer perceptron, a basic neural network, because that's what it usually sees in machine learning code. It completely ignores the physical constraints of the specific field it's supposedly coding for.
Okay, so if general AI models fundamentally don't understand the physical constraints of light and space, how do we teach an AI the, laws of physics for this specific coding task? And I think that brings us to the core of a NeRFi. The first major mechanism it uses is something called a context-free grammar, or CFG.
Right. So to prevent the AI from just hallucinating these incorrect software architectures, NeRFify leverages an established open source framework called NeRF Studio.
Okay, I've heard of that.
Yeah, NeRF Studio acts as this highly modular standard library for building NeRFs. So by formalizing NeRF Studio's rules into a context-free grammar, NeRFify Y creates a strict set of structural laws for the code generation. The AI is structurally constrained. It can only generate code that satisfies the underlying architectural invariants of that framework.
So it's kind of like asking an AI to design a house. If you just give it a blank canvas, it might put the plumbing in the ceiling or design a staircase that just leads nowhere. But by using a context-free grammar, it's like giving the AI a strict architectural blueprint first, so it physically cannot generate a door that doesn't connect to a room.
That is a perfect analogy. The grammar ensures that the data manager component properly connects to the rendering pipeline, which connects to the spatial field, which connects to the optimization model. It forces the language model to color inside the lines of a proven software architecture.
Makes total sense.
But that blueprint is just the foundation, right? The second major innovation dictates how the code is systematically written, and it uses this multi-agent process called graph of thought synthesis.
Graph of thought. Because typically, when we think of an AI generating text or code, we picture it typing top to bottom, streaming tokens one after another. But NeRFify doesn't do that, does it?
No, not at all. Instead of writing code top to bottom, a master agent orchestrates these specialized file agents to build a repository in topological dependency order.
Break that down for me.
So think about how complex software works. File A might depend on functions written in file B, which relies on data structures from file C. If you force an AI to write file A first, it is blindly guessing what file C will eventually look like.
Right, which leads to bugs.
Exactly.
Yeah.
The graph of thought process eliminates this guessing game by breaking the coding process into 4 rigorous phases. So phase 1 is DAG construction. DAG stands for Directed Acyclic Graph. The master agent basically maps out the paper's requirements into a strict roadmap of dependencies.
Wait, so it's not just generating a wall of text. It builds a DAG to map dependencies. But if academic papers don't explicitly list their software dependencies, how does the AI even know what that roadmap should look like? Isn't it just guessing based on keywords?
It would be guessing if it relied solely on the main text. But the master agent is specifically prompted to cross-reference the paper's mathematical methodology with that context-free grammar we just discussed.
Oh, I see.
Yeah, so it identifies which equations map to which structural components, like, matching a specific loss function to the optimizer component, and it draws the dependency arrows accordingly. And once that roadmap exists, it moves to phase 2, the interface freeze.
The interface freeze, that sounds like a concept pulled straight out of enterprise software development.
It operates on the exact same logic. Before writing the actual algorithmic logic, the subagents establish the API contracts between the files. They essentially agree on what specific data structures will go in and what shapes will come out.
So it's actively forcing different AI subagents to negotiate the contracts of their code before they even write the specific functions. How does that practically prevent the code from crashing later on?
It prevents circular dependencies. In poorly planned code, file A needs data from file B to compile, but file B needs data from file A. The compiler gets trapped in an infinite loop and crashes.
Right.
By freezing the interfaces first, the agents guarantee the topological flow of data is strictly one way. Once those contracts are locked, we enter phase 3, which is implementation. The agents actually write the mathematical logic inside those pre-approved boundaries.
And crucially, they do this with strict tensor shape and gradient checks, right? Because in computer vision, you are constantly multiplying matrices. If a 3D matrix is accidentally treated as a 2D matrix, the math fails silently until the whole system breaks down.
Exactly. The agents are validating those matrix dimensions continuously. Which brings us to phase 4, integration testing. The framework compiles the code in real time. If there is a syntax error or a missing import statement, the agents run automated repair and smoke tests to patch it immediately.
It functions like an entire software development team, including the quality assurance department, contained entirely within the framework.
Yes, exactly.
That is wild. It mirrors the human debugging loop perfectly, but executed at machine speed. So that covers how it writes the code, but reading an academic paper presents its own massive hurdle.
Oh, absolutely.
Because here's where it gets really interesting. Academic papers rarely explain everything from scratch. You'll be reading a dense methodology section, and the authors will casually write, "We adopted the distortion loss from MIP-NeRF 360, and then just move on to the next paragraph.
Right, because researchers assume you have read the last 5 years of literature. A generic AI reading that sentence will either invent a fake mathematical formula for a distortion loss, or it will just leave a placeholder comment in the code saying, insert distortion loss here.
Which is useless.
Completely useless. NeRFify circumvents this with an innovation called compositional citation recovery. It essentially operates as an automated research detective.
But pulling a citation is one thing. How does it know which part of the 30-page reference paper contains that specific distortion loss formula? It can't just dump the entire text of a second PDF into the code it's writing.
No, the mechanism is highly targeted. When the framework encounters a reference to a prior technique like the MIP-NeRF 360 distortion loss, it actively traverses the academic citation graph. It queries databases like ArcFIF, retrieves the source code or the LaTeX files of the referenced paper, and searches for the specific mathematical context surrounding the keyword. It extracts just the missing implicit dependencies, the exact mathematical formula, translates that LaTeX math into PyTorch code, and integrates it into the current implementation.
So it's literally hunting down the missing pieces. That solves the issue of missing math. But even if the code compiles perfectly, and even if it correctly sourced all the unwritten formulas, we are still dealing with visual rendering. A program compiling doesn't guarantee the 3D scene actually looks correct.
Compiling is a very low bar. To ensure the final output visually matches what the paper promised, NeRFify utilizes a fourth major innovation, the critique agent.
The critique agent?
Yeah, it actively runs a training iteration on the synthesized code, renders a novel 3D view, and visually analyzes the output image.
Mind-blowing. The AI is essentially acting like a human researcher, compiling the code, staring at the blurry output image, identifying the visual flaw, and going back into the code to fix the math. But how does it evaluate visual quality in a way that translates back to fixing Python code?
The critique agent utilizes vision language models, or VLMs, to visually diagnose artifacts. And it doesn't just look at the whole image. It uses a technique called PSNR minima analysis.
What is PSNR?
PSNR stands for peak signal-to-noise ratio. The agent scans the rendered image to find the specific regions where the visual quality drops the most. These are the minima. Then it applies cross-view geometric validation to understand the root cause of the flaw.
Let's expand on that cross-view geometric validation, because if the VLM spots a dark, blurry patch on the front of our glossy apple, does it actually move the virtual camera to the side to investigate?
It does exactly that. It shifts the viewing angle. If the dark patch remains fixed in 3D space as the camera moves, the AI knows there's a physical geometry error. It accidentally generated a floating black blob.
Ah,
Okay. But if the dark patch changes or disappears from a different angle, it knows the geometry is fine, but the view-dependent lighting calculations are flawed.
wow. So once it identifies whether the bug is in the physical geometry or the lighting math, it connects that visual flaw back to the corresponding Python file and iteratively patches the equations until the rendering improves. It is literally acting as a visual debugger.
It is. Furthermore, it features a fifth capability called knowledge enhancement. During this iterative patching phase, it can actually apply novel software optimizations that weren't even included in the original paper.
Wait, really?
Yeah, it can structure the memory management to run faster or cleaner than the original authors envisioned.
Okay, we have covered a massive amount of theoretical ground here, but I really want to ask for the hard evidence. How do we know this multi-agent orchestra actually works in the wild and isn't just some clever parlor trick?
Well, the researchers proved its efficacy by creating NeRFify Bench. This is a comprehensive evaluation framework that tested the system across 30 diverse NeRF papers. They divided the papers into different sets to isolate specific capabilities. But the most critical evaluation is set 1, which consists of 10 never-implemented papers.
Let me push back on the methodology here for a second. If a paper already has an open-source GitHub repository, a skeptic would easily argue that the foundational language models just memorized that code during their initial training phase. It wouldn't be synthesizing anything, you would just be regurgitating internet data.
And that is precisely why set 1 is so important. Those 10 papers had absolutely zero publicly available source code anywhere on the internet.
Zero.
Zero. To create a baseline for comparison, the researchers had to hire human domain experts to spend weeks manually implementing the code from the PDFs. Because the code never existed publicly, it is mathematically impossible for the underlying LLMs to have memorized it during pre-training.
Which proves it's actually synthesizing, not regurgitating.
Exactly. It isolates the test and conclusively proves that NeRFify is actively building complex software architectures from scratch.
So let's look at the head-to-head results. You have human experts who spent weeks writing this code compared against the NeRFify system. What were the execution stats?
NeRFify achieved 100% executability across the board. Every single implementation it generated compiled, ran, and trained successfully without manual human intervention.
And keep in mind, the generic baseline models failed 95% of the time on those same tasks.
Exactly.
Achieving 100% executability is a massive leap. But did the 3D scenes generated by the AI's code actually look as realistic as the ones built by the human experts?
The visual output was nearly identical. When measuring the PSNR, that peak signal-to-noise ratio, NeRFify's output was within 0.5 decibels of the human expert's output.
Wow.
They also used the SM metric, which stands for Structural Similarity Index Measure. SM evaluates perceptual structure. It basically asks, does a straight edge actually look straight to the human eye? On that metric, the AI was within 0.02 of the human baseline. To a human observer, the 3D environments generated by the AI's math were visually indistinguishable from those generated by the human's math.
And most importantly, it reduced the implementation time from weeks of agonizing labor down to just minutes.
And the implications for the listener, for anyone interested in AI, are profound. Why should you care? Because this democratizes AI research. Historically, testing a highly theoretical, bleeding-edge paper required a team of postdocs, months of funding, and massive computational resources just to see if the proposed math actually functioned.
You essentially had to take the author's claims at face value until you spent a month building the system yourself.
Exactly. But by collapsing that barrier to entry, tools like this accelerate how fast the entire field of computer vision can move. You no longer need a team of postdocs. You can read a dense theoretical paper over breakfast, have the framework synthesize the source code during your morning commute, and be running experiments on that architecture by lunch.
It ensures that complex mathematical contributions become usable, testable tools for the entire community instantly.
We are transitioning away from a paradigm where research progress is bottlenecked by manual software implementation. We're entering an era of rapid compositional research, where theoretical ideas can be validated and iterated upon at the speed of computation.
Which leaves us with a really profound, forward-looking question. If we now have AI multi-agent frameworks that can read a highly theoretical physics or math paper, hunt down its implicit citations across the internet, construct complex software architectures, visually test the output, and optimize the underlying results. What exactly is the role of the human researcher in the next 5 years? Are we looking at the dawn of automated end-to-end AI scientists that can peer review, research, and out-innovate their own human creators?
It certainly feels like we're standing right on the edge of that frontier.
Thank you for listening to this episode. If you enjoyed the discussion, please subscribe to our podcast for more deep dives into the world of artificial intelligence.